Hi, AP Physics. I am going to go over the AP Physics 1 midterm review questions, and we'll start with question number 1. An object is thrown with initial velocity v near the surface of the Earth, and if it's thrown upward, they're asking what's the direction and magnitude of its acceleration. Now, the most common mistake here is simply confusing velocity with acceleration. So if I were to draw a motion map, the idea is that velocity is slowing down until it stops at the very top. However, even though velocity is decreasing, the amount it's decreasing by is constant. And that's what we call gravity, of course. There's, of course, gravity even at the top, but therefore it is going to be downward and constant. If the object is thrown horizontally, even if it's thrown horizontally, you have to understand that if you were to draw a motion map, the velocity on the x-axis stays constant, while the velocity on the y-axis increases by a certain amount. But that's velocity. If we're asking about how much it's increasing by, the same idea here is if you have a falling object, gravity is pulling it down at every single point. So therefore, that's going to be downward and constant as well. For the next question, what is inertia? Don't confuse inertia with force. Inertia is part of Newton's laws, where we talk about Newton's first law is the law of inertia. But that's with the understanding that inertia is defined as a resistance to any change in motion. And of course, that resistance to any change in motion ultimately is dependent on the amount of mass that it has. So that inertia, whether you're in outer space away from any sort of gravity, even if you're completely free of a gravitational field, you still have mass, you still have inertia. That's why if an astronaut were to push on a spaceship in outer space, he wouldn't really be able to push the spaceship that much because it's so massive and has a great resistance to any change in motion. For number 3 here, we have a velocity question along with an energy question. Number 4. They ask, after the block is released, in which of the following sequences of positions is the speed of the block ordered from fastest to slowest? Well, it's mostly with the understanding here that if you were to identify the energies, at the very top, you'd start with from rest and be with height to be EG. At the bottom, at B, there's no more height, so therefore it's all EK. But at C, it's a little bit of height. So it might be 1 bar of EG and 2 bars of EK. At D, it's a little bit more height, so it'd be 2 bars of EG and 1 bar of EK. And E would be in between B and C. So if we're talking about when it has the most kinetic energy, we're talking about point B, then E, then C, D, E. So, but for our cases, it's going to be B, E, C, D, so it's choice B. What is the direction of the net force on the block when it is positioned at C? Well, this is circular motion, and circular motion ultimately is about the net force. So therefore, the net force, because it is a circle, it has to be pointing towards the circle, center of the circle. So the answer is choice C, pointing to the left only. And when we're talking about the gravitational energy, we're talking about when is the gravitational kinetic energy most nearly equal. So if you want it to be most nearly equal, if we assume at the very beginning, at A, that there were 4 blocks of EG, then if you want it to be equal, at the next position, it will have to be 2 blocks of EG and 2 blocks of EK. So if you want 2 blocks of EG, that literally means that's half the energy or half the height. And half the height would be from here to here, point C. A 3 kilogram block hanging from a spring scale is submerged in a beaker of water until the spring scale reads 20 newtons. So right now, if we take a look at our force diagram, with the spring scale holding it up, we have the weight of the block going down, but we know that it has to be balanced because it's not moving. So if they ask us how much buoyant force is acting on the block, there must be an additional 10 Newton force pointing up over there. Choice A. A planet of mass m orbits a star, and if the orbit is circular with a radius r and period of t, which of the following is basically true? Okay, so if they're asking us in part 1, or choice 1, what's the speed of the orbit, assuming it's circular of course, we know that speed is equal to distance over time, but the distance of course around a circle is called the circumference. So that's equal to 2 pi r over the period. So choice 1 is okay. If we're asking about the gravitational force is Fg equals to g m1 m2 over r squared. That's simply knowing the formula and of course recognizing that's on your reference table. So the gravitational force acting on it has to be according to the formula. So again, that's true. They're asking if the orbital radius r were greater, then the period would also be greater. Now, but what does the radius have to do with the period? This one's actually a complicated question over here. So let's first, of course, recognize the fact that gravitational force is acting as the centripetal force. So if I set the formula for gravitational force equal the formula for centripetal force, we can see that the radius crosses out over here and the mass of the small planet is canceled out as well. In fact, the velocity, square root both sides, is also ultimately equal to g, the mass of the star, divided by the radius of its orbit. So if you increase the speed, if you increase the radius by a certain value, you're ultimately going to be decreasing how fast it's going because there's not as much gravitational force to be pulling on it. So with that in mind, v is equal to 2 pi r over t, and I rearrange it to 2 pi r over v. If I increase the radius and I decrease the speed, ultimately if I plug in numbers, you would see that the period would increase as well. So you might have learned that in earth science with one of Kepler's laws, but basically all the statements are true. An object attached to one end of a string moves in a circle at a constant speed. Which of the following is correct? Now, it cannot be choice B because velocity includes a direction, and the direction is changing. It cannot be choice C because anytime you have circular motion, you have to have a centripetal force. And if the string breaks, assuming it's going in a clockwise manner, whenever the string breaks, it's always going to fly off in a direction tangential to the circle. So if it was up here, it fly off in a straight line. If it was over here, fly off in a straight line. Over here, fly off in a straight line. Radially means it flies away from the circle, which is wrong. And it will definitely not keep its circular motion. So the fact is, ultimately, because it is changing direction, the velocity is changing, so therefore there must be an acceleration. Number 10 is a projectile motion question. They say a ball is thrown with an initial velocity of 20 meters per second, an angle of 60 degrees. They ask, what is the velocity at the top? Well, if you draw a motion map, we'll understand that, of course, the velocity on the y-axis gets smaller and smaller as it gets to the top. In fact, it stops at the top and then comes back down with a vertical velocity. Meanwhile, the horizontal velocity stays exactly the same. So when they ask us, what is the speed at the top, the only speed there is x velocity. So to find the x velocity, cosine 60 equals to Vx over the hypotenuse of 20. So Vx equals to 10 meters per second. Or choice D. A block of mass 3 kilograms slides along a horizontal surface that has a rough section, which means, of course, there's friction and there's energy being dissipated. They ask us, what is the amount of work done by the frictional force? Well, if I were to draw an LOL diagram, I could draw like this. We know that we have 4 bars of EK. And then because of the ground acting on the block, I end up with maybe only 2 bars of EK, but 2 bars of E dis. And E dis is basically the same thing as the work done by the frictional force. So I really end up with EK1 is equal to EK2 plus E dis, which is the work of friction. So we have 1/2 mv1 squared equals to 1/2 mv2 squared plus E dis. Masses do not cancel out because there's not a mass in every single section. But I end up with 1/2 times 3 times 5 squared minus 1/2 times 3 times 3 squared. And I end up with an answer of 24 joules. So the answer to number 11 is choice A. And then when they ask us, what's the amount of frictional force that was applied to it? Well, if we're looking for the frictional force, that means that we have to use a little bit of kinematics here. I would want to try to set this equal to friction times distance, but I don't know the distance, so I can't just plug in like that. However, they do tell me that the initial velocity going in is 5 meters per second. The final velocity is 3 meters per second over a time of 0.5 seconds. So if you look at the information that's given, you can solve for the acceleration. A is equal to 3 minus 5 over 0.5, so equals to negative 4 meters per second squared. And assuming, of course, that in terms of block moving, the only force on the x-axis is friction, then friction is equal to mass times acceleration, which equals to 3 times negative 4, which ends up equaling to 12 newtons. In a lab, a block weighing 80 newtons is attached to a spring scale and both are pulled to the right. Assuming that it's because it is a horizontal surface, Fn will also equal to 80 newtons. They say friction is negligible. They ask, what is the acceleration of the block? Well, then if this is the only force pulling it forward, then F net is equal to ma. The force pulling it is just equal to ma. So the spring scale reads 32 newtons. The only tricky part here is we have to figure out what's the mass, but if you know the weight is 80, the mass of course has to equal to 8 kilograms times A, so the acceleration is 4 meters per second squared. A student weighing 700 newtons climbs at constant speed to the top of an 8-meter vertical rope in power. So this is just understanding the power formula is equal to force times distance over time. The student is climbing up the rope himself. So ultimately the force that he has to pull upwards is going to equal to his weight, so otherwise he wouldn't move up. So we end up with 700 newtons times 8 meters over 10 seconds, which equals to 560 watts. Choice C. And when they ask about units of power, well, power is equal to work over time, so it equals to joules per second, which I also mentioned is the same thing as watts. But the question is, what's a kilowatt hour? Well, if we break it down to each parts, a kilowatt is really just a watt, 1,000 watts. So this kilowatt is actually already power. Hour, of course, is time, and power times time is simply equal to the amount of energy that was used. So choice 3, kilowatt hour is actually a unit of energy, so the answer would just be choice 1 and 2, or choice C. 3 forces act on an object. If the object is in translational equilibrium, which of the following must be true? Equilibrium ultimately means that it is balanced. So that means the vector sum of the 3 forces must equal to 0, which is true. They ask, do the magnitude of the 3 forces have to be equal in order to be in translational equilibrium? I mean, it could be equal. We could have one force here, and one force down, and all 3 forces would cancel each other out, assuming they're the same. But they don't have to all be equal. I could have a 5 going here, a 6 going here, and 11 going the other way. So in this case over here, they are not equal forces, so it can't be choice 2. And this example over here, they're not parallel, so it can't be choice 3. The only answer that makes sense is choice A. Number 17 is a spring that's oscillating back and forth. So if you imagine on a frictionless surface, okay, this block is pushed in and compresses a spring, and it's let go, which means it then bounces back and forth. And as it's going back and forth, you can see that in the middle, it's going the fastest, and at the ends, it stops before it changes direction. So therefore, in terms of kinetic energy, we can see that there's the most kinetic energy in the middle, and there's no kinetic energy at the ends. So therefore, the answer is choice D. I would like to point out, however, just in case you're not sure where this graph comes from, that at the ends, the spring is most compressed or most stretched. So you have the maximum amount of elastic energy stored in the spring at the ends, but in the very middle, it's not stretched or compressed at all. So therefore, there's no energy in the middle, which is what that graph shows. I would also like to point out that this graph represents the total energy in the system, because if I were to graph the elastic energy in there, it's just an inverse of the kinetic. Basically, when you add the elastic energy plus the kinetic energy, it equals to the total, which stays the same the entire time, assuming that there's no energy lost from the system. In this case over here, it's a little bit tricky because they ask what rate does a child do work? So they're not asking about energy. Rather, they're asking about power. They give us a bunch of variables of a mass, a speed, and a coefficient of friction. Well, first of all, if they are giving us a speed, and it's a constant speed, well, our formula for power is either work over time or force times velocity. In this case, we'll probably want force times velocity. But that doesn't look like any of our answer choices. So let's take a look. It's moving at a constant speed, so Fn will equal to the weight, and the force going forward will equal to the friction going back. And if friction is equal to mu times Fn, Fn is simply the weight, and the force is equal to that. So when we're talking about the force being applied, we're talking about mu mg, because it's balanced. So it ends up with mu mg times velocity, which is choice A. An object has a weight when standing on a planet with a radius r. The weight is just a fancy way of saying gravitational force. And they ask us what happens to a gravitational force when you move away. Well, of course, the gravitational force formula between two objects is g m1 m2 over r squared. Now, the way I usually like to think about a multiplier question, I just make everything equal to 1. 1 times 1 times 1 over 1 squared. And if I move 4 times farther away, I end up with 1/16, which is meaning I am 1/16 the weight that I was before. Choice E. What is the kinetic energy of a satellite of mass m that orbits the Earth? Now we know kinetic energy is 1/2 mv squared, but we don't have a speed. So this one's a little bit tricky. If you look at the answers, you see big G, which basically implies that they want us to look at Fg equals to G m1 m2 over r squared. And we know that it's a circular orbit. They mention that on purpose, meaning that that gravitational force is acting as a centripetal force. So if you notice, this is what we did before in an earlier question. The speed of Earth is equal to G times the mass of the Earth divided by the radius of the Earth. So if v squared is equal to g m over r, all I really have to do is replace 1/2 m times g m over r. And we end up with choice B. So that one's complicated because you're substituting one formula into another formula. But if you break it down, we know the formula for kinetic energy, we know the formula for gravitational energy. How do they relate? And they end up relating by the speed. In which of the situations would an object be accelerated? So acceleration, of course, means a change in velocity. And velocity can change either by speed or by direction. And therefore, it cannot be choice 1, constant speed in a straight line. But circular motion is constant speed, but it's changing in direction. Well, a projectile, of course, has gravity acting as acceleration. So the answer would be choice D. A ball falls straight down through the air under the influence of gravity. There's a retarding force F on the ball, which is given by BV. So they ask, what's the acceleration? Well, let's draw a force diagram first. The ball, of course, is pulled down by its own weight. And they're saying the air resistance force is represented by B times the velocity. So what's the acceleration? Well, it is moving down, so I'll make down positive. So when I do F net is equal to ma, I end up with mg minus bv is equal to ma. Now, this almost looks like our answers, but if you notice, if I divide by mass here, I have to divide by mass here and divide by mass here. So these masses cross out, these masses cross out, this one gets left behind. So I end up with G minus BV over M. Choice B. An ideal spring obeys Hooke's law, which of course means that the force of the spring is directly proportional to the amount that's stretched or compressed. And we have a spring that ends up being stretched 0.075 meters when a mass of 0.5 kilograms is hung on it. They ask, what is the value of the spring constant? Well, Fs equals to Kx. The force that's pulling down it is the weight of the block, so that's 5 newtons, which equals to K times the amount stretched. It's not the original length of the spring or the new length of the spring, it's the actual amount stretched, which they give us, which, using your calculator, you end up with 66.67 newton per meter. In other words, choice E. Now, the key point for this question here is the word rough. Because it's rough, that means, of course, that there's going to be friction, which means that there's going to be energy being dissipated. So when they release the ball from point P and they ask how high is going to end up on the other side, it's not going to go exactly to the same height as it was before, unless the energy was perfectly conserved. Now, how much energy is lost? We have no idea. So we end up choosing choice E. It's between 0 and h, but it depends on how much energy is lost due to friction. An object is released from rest from a planet that has no atmosphere, so there's no air resistance. So the initial velocity is 0. It falls for a height of 3 meters in the first second. They ask, what is the acceleration? So we just end up with delta y equals to VOT plus 1/2 AT squared. No initial velocity. 3 is equal to 1/2 A times 1 squared. So you can just, A is equal to 6 meters per second squared. Or choice C. Spacecraft X has twice the mass of Y. Then which of the statements are true? Okay, so because it's twice the mass, if we're talking about gravitational force on Earth, well, that's simply mass times gravity. So mass is directly proportional to the gravitational force. So with twice the mass, that's twice the gravity. On the moon, X has twice the weight of Y. Well, weight is just another fancy way of saying gravitational force. So with twice the mass, twice the weight. When both are in the same circular orbit, X has twice the centripetal acceleration as Y. Now, centripetal acceleration, don't confuse with centripetal force. Centripetal acceleration is V squared over R, while centripetal force, which is really F net, is equal to mv squared over R, or m times A. So ultimately, for the acceleration, it's just based on the change of velocity. It's not based on the mass itself. So 3 does not count. So the answer would be choice C. 27 is similar in that you have two spheres with equal densities, subject only to their mutual gravitational acceleration. Okay, so because they're attracted by the same force, which is really Newton's third law, they feel the same gravitational force, and that's the answer actually. Now, it can't be the other ones because it won't be the same acceleration. A big mass will have a small acceleration, while a small mass will have a big acceleration. They won't have the same velocity because they're accelerating differently. Their kinetic energies won't be the same because they have different velocities. The only thing that will end up being the same is the gravitational force, and actually also their momentum, although it would be in opposite directions. Over here, it's going at constant speed through a smoothly curved surface. Notice this is really a circular motion question. So therefore, you have a centripetal acceleration with a tangential velocity. So you end up with choice B. Here we have a connected objects question. Okay, and with a connected objects question, it's easier if you always pretend that it's one object. So I'm going to take that 3m and kind of strain it out and connect it to the m as pretend it's just one object. And you have to say to yourself, what's pulling it forward? What's holding it back? So pulling this whole object forward, you have the weight of the small block. Because this weight over here is not on the axis of motion, it doesn't do anything. In fact, it's balanced by the normal force. So I don't worry about the tension at all because tension is in here. I don't care about that. So because this total mass is 4m, if I do F net is equal to ma, I have mg pulling it forward. The mass of the entire system is 4m times a. Or just add the masses. The masses cross out on both sides. Divide by 4, divide by 4. Acceleration is 1/4 that of gravity. A car traveling north turns left along a circular curve. Okay, and the package on the seat slides towards the right. Which of the following is true of the net force on the package? Well, when you have a car driving north, and there's your package inside, and it turns. As the car is turning, the package wants to keep on going in a straight line. That is its inertia. So it wants to go in that direction, and it ends up getting pushed against the right side. So there's nothing actually pushing to the right. It just slides to the right because there's not enough centripetal force towards the center to hold it in place, which means the answer is choice E. Okay. There is no force pushing it to the right. There's no centrifugal force. There's no force pushing it to the north. It's its own inertia. And these are questions 1 through 30. Mr. Blaney will be doing the rest.